Hello everyone. Welcome to ComSci 191 Special Topics Computer and Network Security. Today we are going to discuss about cross-site scripting. At the end of the session, you should be able to define cross-site scripting attack and its types, explain how to launch XSS attacks, and discuss the countermeasures for the attack. Cross-site scripting, or XSS, is a type of injection attack where malicious scripts are injected into trusted websites and uses it generally in the form of a browser-side script to a user. With that, the attacker can steal a victim's credentials, such as session cookies, tokens, or any sensitive data retained in the browser. There are two types of XSS attacks: the non-persistent or reflected, and persistent or stored XSS attack. The non-persistent or reflected attack involves websites with reflective behavior that does not sanitize user inputs properly. For instance, when a JavaScript code or a malicious code is injected in a website's input, that becomes a part of the website's response. Let's say example.com is a website that accepts user input for searching. When we type an input, for example XYZ, and we click the search button, the website responds with the message "No results for XYZ." If you notice, the user input is reflected in the website's response. Also, assuming that the website uses the GET request, the user input will also be included in the URL. Now let's try to replace the input XYZ with a JavaScript code. Let's say an alert statement. If the website does not sanitize their input, when we click the search button, what do you think will happen? The JavaScript code will actually be executed. An alert box will appear containing the value attack. Aside from being executed, the malicious code is now part of the URL. So if we send that URL to a user, when the user clicks the link, then the malicious code will be executed in the user's browser. And that is the non-persistent or reflected XSS attack. The figure here shows how the non-persistent XSS attack works. The attacker will trick the victim to click the link injected with malicious code. The user will open the link, and then the website will send a response to the user. With the malicious code injected, sensitive data can be sent to the attacker. The persistent or stored attack involves directly sending the malicious code to the website, which is stored in a persistent storage, such as in a database, message forum, user profile, or comment field. The attack happens when a user accesses the web page with the malicious code. This is more powerful than the non-persistent XSS attack because the malicious code is stored in the database and affects any user that will access the web page with the malicious code. This figure here shows how the persistent XSS attack works. The attacker injects the malicious code to the website. The user accesses the website, and the website then will send a response to the user. With the malicious code injected in the visited website, sensitive data can be sent to the attacker. Here's an example of a persistent XSS attack where a malicious code is injected in a Twitch chat software. One popular instance of the persistent XSS attack is the Sammy Worm by Sammy Kamkar last 2005, where millions of MySpace users got affected by an injected code in Sammy's profile. Whoever sees his page automatically adds Sammy as a friend and puts Sammy as my hero in their profile. Additionally, it is a self-propagating worm where the malicious code is also copied to the victim's profile. The XSS attack can cause a serious damage to its victims. It can cause web defacing, where the injected code can make arbitrary changes to a web page by accessing its document object model or DOM nodes. It can also spoof requests, where the injected code can send HTTP requests to the server on behalf of the user. In the case of SammyWorm, the code sent out HTTP requests to MySpace of adding a new friend to the victim's friend list. Also, it sent out a request in changing the victim's profile. XSS can also steal the victim's private information through the injected code. For the lab setup of your exercise, you will use ELG, which is an open-source web application for social networking with disabled countermeasures for XSS. The website is locally hosted, so you can already access it in your seed VM. It is mapped to the URL www.xsslabelg.com. It should look like this. There are 5 user accounts created for this website. the admin, Alice, Bobby, Charlie, and Sammy. The goal for this exercise is to copy what Sammy has done before. So how do we launch an XSS attack? First, we find places where we can inject the JavaScript or malicious code. One usual location is an input field. In ELD, there are several input fields in the profile page where we can inject the code. If we try to inject a JavaScript code into a web application and the code is executed, it means that it is vulnerable to XSS attack. I will not be discussing the lab tasks 1 to 3, so please make sure to accomplish it first before you continue to listen to this discussion. In Sammy's hack, he added himself to other people's friend list without their consent. For this exercise, we want to do something similar. Using Sammy's account, we will put the malicious code in the About Me section of this profile. After that, we will log in as Alice and visit Sammy's profile. The code will not be displayed but will be executed. The code then sends an add friend request to the server. And if we check Alice's friend list, Sammy should be added. To launch the attack, we need to understand how the targeted website works. We need to understand how the website sends out an add friend request and the parameters needed, since we will use it to create the malicious code. To investigate, we need to create another account. Let's say we created Charlie's account. Using Charlie's account, we go to Sammy's profile. Let's open the HTTP header live extension to be able to inspect the HTTP header fields. Click the Add Friend Request button, and from that, let's capture the created Add Friend HTTP request. Most of the lines here in the HTTP header are standard, except for those that are marked. Number 1 is the HTTP request to add Sammy as a friend. It contains the ID of the friend that should be added to the friend list. The value is set to 47, which is Sammy's ID. There are two other parameters, LTS and LToken. We need these values or else our request will be discarded. These values are page specific, so we will need to find the correct values during runtime. The main challenge here is finding the correct values of LTS and LToken parameters. Without them, the website will discard the request. Another parameter is the session cookie. The session cookie here is Charlie's. When another user, let's say Alice, sends a friend request, the value will be different. The browser is the one that sets the cookie of an HTTP request, so we do not need to worry about this. Now let's try to find the values of the two parameters LTS and LToken. In the current web page, let's right-click it and select View Page Source. We can see that the two values are already assigned to two JavaScript variables in ELD, the eld.security.token.lts and eld.security.token.ltoken. This makes it easy for us to execute the attack because we can just use these variables to get the values. Knowing the necessary values, you can now create the malicious code. Our next task is to put the statement Sammy is my hero in other people's profile without their consent. Using Sammy's account, we will put the malicious code into his profile and wait for others to visit his page. Let's use Alice's account to view Sammy's profile. As soon as Sammy's profile is loaded, the malicious code will get executed. Lastly, on checking Alice's profile, we should see that Sammy is my hero is added to the About Me field of her profile. Now we will not discuss it in detail anymore, but just like in the previous task, we need to understand how the edit profile service works and the parameters needed. Using Sammy's account, let's capture the edit profile by clicking Edit Profile and editing the About Me field. When we inspect the captured HTTP request, the URL of the edit profile will look something like this. The edit profile uses a post request, so no fields can be seen in the URL. The session cookie, which is set by the browser, is there, and so are the parameters LTS and LTokens. The text we put in the About Me field is assigned to the description field. Every field has an access level. As for the description, it has an access level 2, which means that the field is viewable to everyone. Lastly, the user ID is there. The user ID shown is Sammy's, since we changed his profile. Knowing all the necessary values, we can already create the malicious code. Another task in our exercise is to write a self-propagating XSS worm. Using Sammy's worm, not only will the visitors of Sammy's profile be modified, their profiles can also be made to carry a copy of Sammy's malicious code, so when an injected profile is viewed by others, the code can further spread. But the question is, how can JavaScript code produce a copy of itself? There are two approaches to do that, the link and DOM approach. The link approach is done when a JavaScript code can be included in a web page via link using the src attribute of the script tag. On the other hand, the DOM approach is done when a JavaScript code can get a copy of itself directly from the DOM via DOM APIs. For the exercise, you will be required to use the DOM approach since it is more challenging than the other one. There are some countermeasures that can be used against XSS attack. One is the filter approach, where the script or code is sanitized or removed from the user inputs. However, it is difficult to implement since there are many ways to embed the code other than the script tag. Instead of developing one, it is suggested to use well-vetted filters. There are several open source libraries that can help filter the JavaScript code. For example, JSoup, which provides an API called Clean to filter out JavaScript code from data. Another countermeasure is the encoding approach, where the HTML markups are replaced with their alternate representations. The JavaScript code is encoded before being sent to the browsers. The code will now be displayed instead of being executed. For example, if the attacker uses a script tag, the angle brackets will be encoded. Elg also created its own countermeasure. It uses a module and a function to sanitize and encode the input provided by the user. And that's all for our topic today. Here are the references used for this discussion. If you have questions, feel free to send me a message.